Welcome back. So, in the last class we have looked at type 1 alloys called isomorphous alloys, which means both the components are completely soluble in liquid state as well as solid state. And today here we are going to see a few variations of type 1 alloy. When we saw the type 1 alloys phase diagram, here I am drawing it again on the y axis. Here you have, let us say, A and B, and let us say melting point of A is lower than the melting point of B, then the phase diagram of an isomorphous alloy looks something like that. The isomorphous alloys of the kind that we have looked at so far are looking like that, wherein A and B are completely soluble both in liquid state as well as solid state. Now, is it possible to have a maxima or a minima for this liquidus and solidus line? That is the, if we have something like that as we have shown here, you can see that this is also an isomorphous, this left side is also an isomorphous alloy, where the liquidus line has a maxima. On the right hand side here you have a solidus line showing a minima here, right. So, alloys of this kind are also possible, but the alloy composition, for instance, if you look at the isomorphous alloy variations with a minima that is shown in on the right hand side here, we see that the composition at x, let us say you are looking at the x composition, then you can see that. So, for instance, let us now compare the solidification of the alloy x with solidification on A and B. Here when you are solidifying from the liquid state and the A solidifies at constant temperature, right. Just above this temperature it is liquid, just below that temperature it is solid. The solidification happens at constant temperature. For A as well as B, the solidification at constant temperature, whereas for all other alloys the solidification happens over a range. For any other alloy combination, for any isomorphous alloy, the solidification starts at one temperature and ends at another temperature. Now, if you look at this special case of an alloy with composition X, again if you consider the solidification is starting and ending at the same temperature. That means it is behaving like a pure metal in terms of its solidification. Solidification is happening at constant temperature, and such alloys are called congruent melting alloys. That means the solidification happens for these materials at constant temperature, and the composition of the alloy in the liquid state as well as in the solid state after the transformation will not change. So, the end product of a congruent melting alloy is only a single phase alloy. So, here you have liquid phase and it transformed to solid phase, right. So is the case for your pure metals A and B. So, the melting process or the solidification of pure metals is congruent in nature. Similarly, if you have any other alloy system which happens at constant temperature, but in addition to that it does not only happen at constant temperature, but the end product it will be a single phase system. Here it is a single phase solid solution alpha, right. So, since for instance if you see this particular alloy composition X, the melting happens. So, amongst all the alloy combinations between A and B, the alloy X has minimum melting temperature, right, minimum solidification or lowest melting temperature, and hence sometimes so this represents a special kind of a reaction, a special kind of alloy types called eutectic, but it is not eutectic. It looks like eutectic. We will discuss what is eutectic, but it looks like eutectic, but it is not really eutectic. We will discuss the salient difference between a congruent melting phase and then eutectic phase. So, since it sort of looks like a eutectic system, this is also called a pseudo eutectic alloy. It is not a eutectic, but looks like an eutectic alloy. Okay. The materials which show these kind of variations of type 1 isomorphous alloys with a minima or maxima at somewhere in between are not very common, but there are not we do not know many materials which has a maxima like we have shown on the left hand side figure, but there are evidences for alloy systems which show a minima like this as it is shown in right hand side figure. The copper aluminum nickel palladium systems are known to show this minima, and there are no known systems with maximum. Okay? All right. So, now having discussed the type 1 alloys, now let us discuss the next type of alloys called type 2 alloys. How did we define type 2 alloys? Type 2 alloys are characterized by the fact that they are completely soluble in liquid state, but completely insoluble in solid state. So, they are completely soluble in liquid state and completely insoluble in solid state. So, that means what? When you are having in the liquid state, they are a nice liquid solution, but when you are solidifying, after solidification they separate out into two different components. They will not make a solution, they segregate into A and B separately. That is what you mean by complete insolubility in solid state. This is a model system that we are choosing to study, because in reality, strictly speaking, no two metals are completely insoluble in solid state. It is not possible to have complete insolubility. There will be very fractionally tiny amount of solubility may be there, but for all practical and hence strictly speaking we cannot say that there is complete insolubility in solid state. But if the solubility is very small, then you can sort of idealize that as complete insolubility in solid state. But even if there is a fractional amount of solubility, that will lead to certain differences that we will see at a later stage. But in this type of alloys, whenever we are saying type 2 alloys, we have complete solubility in liquid state and complete insolubility in solid state. Okay. So, before we start looking at the phase diagram of this kind of type 2 alloys, we will first go through this Raoult's law, which states that the freezing point of a pure substance will be lowered by the addition of a second substance if the latter is soluble in pure substance when liquid and insoluble when solidified. That means, if you have two materials A and B, if they are, let us say you have A, and if you are adding A to B in the liquid state, they are soluble, but A cannot join B in the solid state. If you have a system like that, then Raoult's law says that the melting point of A will be lowered when you are adding B to that, right. The amount of lowering, then the melting point, by how much amount it will be lowered, the amount of lowering is proportional to the molecular weight of the solute. It depends on the molecular weight of the solute. Okay. So, the bottom line is that if you have two materials A and B which are completely soluble in liquid state and not soluble in solid state, then if you take pure substance A and if you add B, then the melting point of A will go down, or the combination will go down in solid state, and if you take B and start adding A, then the melting point of B will also go down. Okay. So, that means if you let us look at the cooling curves. So, let us say this is pure A and pure A solidifies at M, temperature M, and by adding, so pure B solidifies at N, all right. And now when you are adding B to A, so that means it is 80 A 20 B, according to Raoult's law the freezing point has to go down. So, that is why the freezing point has gone down, but it will not solidify at constant temperature, because you will have this is some liquid solution is there, and hence it will solidify over a range of temperatures, right. However, if you, so that means the melting points of the alloys from left to right and the right to left are going to go down because of the addition of the solute atoms to the solvent cloud. And we see that there will be one particular alloy composition at say in this case 40-60 we have shown, wherein again the melting happens at constant temperature. It is like the congruent melting case, like it is like it solidifies, a melting or solidification happens at constant temperature, which means it behaves like a pure metal. Okay. So, So, the cooling curve for pure metal A and B show a single horizontal line at their freezing point here, and as B is added to A, the temperature for beginning of the solidification is lowered. Similarly, as A is added to B, the temperature for solidification is lowered for the alloys coming from the right. Since each metal lowers the freezing point of the other, the line connecting the beginning of the solidification line is called liquidus, should have a minimum somewhere here. So, the minimum point is what is denoted by E, and that point is called eutectic point. That means, of all these combinations of alloys, there is one particular combination at which the melting or solidification happens at the lowest temperature. Okay. So, the composition that corresponds to that is called eutectic composition, and the temperature at which the solidification happens is a eutectic temperature. What do you mean by eutectic? Eutectic is a Greek word. It actually originated from a Greek word called eutectos, which means easily melting. So, as you can clearly see here, this is the alloy that has the lowest melting point, and hence it is called a eutectic alloy. So, this is something that we see in type 2 alloys. So, let us look at the phase diagram from the cooling curves. Now, let us look at the phase diagram, which is temperature composition. So, that is our, let us say, melting point of A, and this is our melting point of B, and as we said, when we start, this is the solidification starting temperature. So, when you are this is our liquidus line. So, M N, so here from the previous figure M N I am choosing, and E is our eutectic point, and that is our liquid solution above that liquidus line, and the melting point of A and melting point of B here as is shown here, and then this green line that we have shown just now, that is MFGN is our solidus line. That means, below that everything will be solid, above that you may have liquid plus solid. So, in between the liquidus line and solidus line you will have two phase region. Above the liquidus line you will have single phase liquid solution, below the solidus line you will have again a solid phase, and it may have two phases, but here we are only talking about a solid phase. All right. So, this temperature at which this eutectic alloy solidifies is called eutectic temperature, known as TE, and this is a liquidus line, and these green lines represent solidus lines, and here you have liquid solution. Since in the solid state the materials A and B cannot mix, right, that is they cannot there is no solubility of A in B and B in A, and hence in the solid state they cannot be called solid solutions, because they cannot solidify each other in one another, right. So, in the solid state we will not have solid solutions, but pure solids. So, that is why we are not representing the solid phases with Greek letters, but we are writing solid A and solid B. It is not a solid solution, it is pure solid A and pure solid B. Okay. So, you will have two, so pure solid A and pure solid B. So, the composition will be only, even though it is a two phase region in some sense. So, but then 100% will be solid A, 100% will be solid B, their weight fractions are going to be different, that we can get it through our tie line that we draw, and this is liquid plus solid A, because the here and here you will have liquid plus solid B. So, left to E you will have liquid plus solid A, because this side the solid is solid A, and right to that liquid plus solid B, because this right side you have B. Okay. And this is our eutectic point at 60 B, right. So, as we have already discussed, MEN is our liquidus line, MFGN is our solidus line, E is our eutectic point, TE is our eutectic temperature, CE that I am calling composition at E is what is our eutectic composition, which is 40 A and 60 B, or we can simply say 60 B. All right. So, this is our phase diagram for type 2 alloys, and so this is our eutectic composition. So, all the alloys left to this eutectic point are called hypoeutectic alloys. This particular alloy at composition CE is called eutectic alloy. All the alloy compositions left to that eutectic point are called hypoeutectic alloys. All the alloys compositions right to the eutectic point are called hypereutectic alloys. Okay. That is a convention that we use in the rest of the module. All right. So, here we can clearly see that the phase diagram has 4 areas to be identified. The area above the liquidus, that is above the liquidus line MEN, this red line is a single phase homogeneous liquid solution, right, L. So, this is a single phase region which is actually a liquid solution of 2 metals A and B, which are soluble completely in liquid state. And there are the remaining 3 areas are 2 phase areas. This is liquid plus solid A is one area, liquid plus solid B is another area, solid A plus solid B is another area, right. This is a 2 phase region. So, this should be solid B, this B here is here. Okay. So, this is a liquid plus solid, so solid A, this region liquid plus solid B, and here you have solid A plus solid B, all 3 are 2 phase regions. Okay. So, in order to find the compositions, for instance, if you want to find the phases that exist in 2 phase region, for instance, if you take this guy, you draw a tie line OP and it touches the liquidus line at P and the solidus line at O, which means the solid in this guy, the solid composition will be solid A 100% A and liquid composition will be corresponding to this vertical, that is about 40, right. So, now let us look at the microstructure evolution of 3 different alloys of type 2. So, type alloy 1 is having eutectic composition exactly, alloy 2 is a hypoeutectic alloy and alloy 3 is a hypereutectic alloy. And let us look at how the microstructures look like for these 3 different kinds of alloys that we have discussed so far. All right. So, as we have already mentioned, above the line MEN solidus liquidus line, you have everything is liquid solution of A and B, and you have 3 2 phase regions, that is liquid plus solid A, liquid plus solid B. This entire region is solid A plus solid B, but here we are showing hypoeutectic alloy region and hypereutectic alloy region. So, above left to the eutectic composition is hypoeutectic, right to the eutectic composition is hypereutectic, both are 2 phase regions. However, there is a slight difference in the microstructure left to the hypoeutectic alloy. So, left to the eutectic composition, that is hypoeutectic alloy, will be a 2 phase mixture of solid A and a eutectic mixture. We will see what do we mean by eutectic mixture, and to the right you will have solid B and eutectic mixture. Okay. So, in order to understand this carefully, let us pay attention to each and every alloy. So, now let us look at alloy 1, the microstructure evolution. So, the alloy 1 is having a composition of 60B on 40A or 60B, let us say, which is cooled from a temperature T0 from say let us 0.1. Okay. So, as you are cooling down from 1, as you are cooling down, what happens? The liquid's temperature, sensible heat, it will be giving away sensible heat. As a result, the temperature of the liquid goes down until it reaches temperature TE, that is your add up to TE in its liquid phase. At TE, at this eutectic temperature, what happens? There is a reaction that is taking place, that is all the liquid would transform to solid A and solid B, because above this it is liquid solution, below that it is again transforming to 2 solids, solid A and solid B, right. So, the liquid upon cooling at TE for this particular composition. So, if you have a liquid solution whose composition is 60B, and when that composition is brought down to a temperature TE, that is this line what we call eutectic line, and at that point the transformation happens from liquid state to 2 solids, that is solid A and solid B, and this mixture of solid A and solid B is called eutectic mixture, because it is going through a eutectic reaction. How does this above such a reaction is called eutectic reaction? So, when we say eutectic reaction, what happens in a eutectic reaction? A liquid upon cooling will transform to two solids, solid 1 plus solid 2. That is the definition of a eutectic reaction. And please note that this eutectic reaction is happening at constant temperature. That means this solidification happens at constant temperature, that is TE. At that particular temperature the solidification happens. So, whenever solidification happens at a constant temperature, we in the previous module when we said the pure metals solidify congruently, that means they solidify at constant temperature. Now, can we call this solidification also to be congruent? We cannot call eutectic solidification congruent, so it is incongruent because of the difference in composition between liquid and individual solid phases. For instance, if you take the liquid solution has 60B 40A, that is the composition of liquid solution, but when it is solidified, solid 1 has 100A, solid 2 has 100B. It has transformed from, it is solidified, but it did not retain the compositions have changed, right, and hence, and it is not a single phase, it is two phase. In the congruent melting alloys, what happens? An alloy solidifies, but it will remain in one phase, but here it is solidified into two phases and their compositions have completely changed, and hence a eutectic solidification, eutectic eutectic solidification cannot be termed as congruent solidification. So, it is incongruent in its nature. Okay. So, now let us look at the microstructures. When you are cooling down just at this point, so when now let us here we are showing the microstructure as an evolution now in the time. At that point TE, initially you have liquid, and as you are cooling it down at that particular temperature, as you are waiting, your initial nuclei of the solid nucleus starts forming, and as you are providing more and more time, the nuclei start growing and complete solidification happens from liquid state to solid state. However, when it is solidifying, what it does when it is solidifying through eutectic reaction, it will form alternate layers of A and B. For instance, in this picture you have the black, so here you have the black region and the white region. So, let us say that the black region is A and white region is B. That means the solidification microstructure looks like alternate layers of solid A and solid B, solid A, solid B, they will be forming alternatively, and such a mixture is called eutectic mixture. That is a typical nature of a eutectic of a solid that is formed through eutectic reaction will have this alternate layer microstructure. So, that is what is usually represented here, and please note that the microstructures that we are showing in these 4 graphs are only representative, they are in some sense they are schematics, they are not the real microstructures, but when you see the real microstructures under the microscope, you may have an alternate layer structure looking similar, but not exactly like that. Okay. Also, the initial shape of the nuclei or grains can be very different. So, here I have only shown 2 grains, it does not mean that in reality also you will have 2 grains, you can have several grains. Okay. So, the moral here, the summary of type 1 alloys, in type 2 alloys, when you are looking at the solidification of alloy 1 which has a eutectic composition, it solidifies at a constant temperature called eutectic temperature, and when it solidifies it transforms into 2 solids, solid A and solid B, and the microstructure will be alternate layers of solid 1 and solid 2, here solid A and solid B. All right. Okay. So, let us see why how this eutectic reaction is taking place. So, let us say solidification is happening. So, let us say at point E, from the liquid a small portion of solid A is formed, right. So, let us say you have the liquid solution, a small portion of, because in the solid state they cannot be mixed. So, this let us say this is A, then what happens, the surrounding liquid would become richer in B, because some amount of A has gone away from that liquid, right. But the liquid's composition has to be, say let us say now this is 60 B, 40 A, 60 B. Now let us say a small amount of solid A has formed. So, the liquid surrounding liquids composition might have changed to 38 A, 72 B, sorry 62 B. That means what happened, everywhere else it is still 60 B, but only the liquid that is surrounding the initial nucleus of A has become rich in B. That means this is not in equilibrium, right, because at that composition all the liquid should be, we have started with a composition of liquid which is having 62 B, 60 B. Now it has become 62, and hence to maintain equilibrium what it will do, it will give away this 2 whatever. So, it will start to maintain equilibrium, some amount of B gets solidified, but it is possible that while the amount of B getting solidified, it might not actually exactly give away 2, it might give a little bit more. So, if B is slightly over solidified, then what happens, from that liquid A gets solidified again, right. Like that A and B try to solidify one after the other in order to maintain equilibrium. So, the process is continued until complete solidification happens into two phases, that is solid A and solid B. And under the microscope the eutectic mixture looks like an extremely fine mixture of two substances. Okay. So, as I have already mentioned, the microstructure is a layered structure with alternate A and B, and the grains these grains that we have seen here grow by adding A to A and B to B until they meet one another. So, here you will start adding A to A and B to B and then they grow. And as we have already discussed, the eutectic solidification is not congruent because there is a difference in composition in liquid and individual solid phases. Alright, now let us look at the solidification of alloy 2 and its microstructure. Okay. So, let us say that so here 1, 2, 3, 4, 5 states and the corresponding microstructures, here they again they are schematics, please keep that in mind. Whenever I am showing it is blue, that means it is liquid. Okay. So, at 1 it is in liquid state, so this is liquid solution, and then the moment you reach point 2, that is on this liquidous line, you would be entering two phase region. That means a small, because you are now you are entering a two phase region, that means you draw a tie line. When you draw a tie line like this at temperature T1, right, and this way I am calling L1 state, then the tie line hits the solidus line here, and that is what that represents pure solid A, and that is the reason why you would form pure A. And what will be the liquid? The liquid composition there, because its A is very small, liquid composition will be almost same 20 B. And now let us say we are further cooling it down, and let us look at the state at point 3 at this position, right. So, this is at temperature T2, then you draw a tie line, the tie line hits the solidus line at this position and the liquidless line at L2. That means the solid composition is again 100 A, because it has hit at 100 A. So, there is 100 A, and what is the liquid composition, that is coming out to be something like 45 B, right. So, here the liquid, initially the liquid is 20 B, by the time it came here it has become 45 B. What happened? The liquid became richer in B, because some amount of solid A is getting out of liquid, and hence liquid starts becoming richer in B as you are coming down. Okay. That means, as you are cooling down, solid A is segregating out and the liquid is becoming a rich solution of B than what it has started off with. And now let us look at situation at point 4 here. At point 4, what happens? You look at you draw a tie line, that will be FE will be my tie line in some sense. So, the liquid, the solid composition is 100A, fine, and now let us look at the liquid composition. What is the liquid composition? Liquid composition is equal to eutectic composition. That means, whatever liquid that is remaining here, the liquid that the remaining liquid has reached eutectic composition, right, the 60B, it has become 60B, that means it has reached eutectic composition. And what is the temperature? Eutectic temperature. Whenever you have a liquid solution at eutectic temperature and having a eutectic composition, what should happen? The liquid solution should undergo eutectic reaction. That means, all the liquid solution should transform into two solids at constant temperature, and that is what happens. All the remaining liquid solution. So, you have some primary A that is formed until 0.4, and between 4 and 5 there is sufficient amount of time which we are not showing on the phase diagram, but remaining liquid solution would transform into eutectic mixture of A and B. That is why you see alternate layers of A and B here, A, B and so on, right. So, the microstructure, if you look at, you have some primary A and a eutectic mixture of A and B, and that is the reason why here in this blue region hypoeutectic alloy, the microstructure is primary A and eutectic mixture of A and B. Please note that the eutectic mixture of A and B is also A, there is also some A in eutectic mixture and there is primary A. Why are we? So, if you take the total weight fraction of A, that will be, there will be some amount of weight fraction that is formed through primary A and some amount will be in the form of eutectic mixture of A and B, alright. So, as you again another thing that I would like to point out, when we are going from 0.2 to 0.3, what is the weight fraction of liquid? It is almost 100% is liquid, only very tiny amount of solid has formed. Now, come to 0.3, what is the weight fraction of solid or weight fraction of A? That will be, so T23, distance T23 divided by T2L2. What is T23? That is 20 divided by 45, right. This distance is 20 divided by 45, that is the weight fraction of A, and weight fraction of the remaining liquid will be I am sorry, the weight fraction of A will be this distance, because the portion that is touching the liquidous line is what we need to take. So, that is 45 minus 20, because this distance will be total distance minus this distance, 45 minus 20 divided by 45, and this is weight fraction of liquid is 20 by 45, that is 15 by 45, now 25 by 45, and this is 20 by 45, right. So, the weight fraction of the liquid has come down and the weight fraction of solid has increased compared to 0.2, and by the time you come to 0.4, what is the weight fraction of the liquid at 4? Weight fraction of liquid at 4 will be 20, because this distance is 20 divided by 60, right, that is 1/3, that is 33.33%. Okay. So, let us carefully look at it now. So, alloy 2, let us go through it once again. Alloy 2 is hypoeutectic alloy of composition 80A and 20B until temperature T1, that is this guy, uniform liquid solution until T1. At T1, liquid L1 is saturated in A. As the temperature is dropped, the excess A must solidify. So, as you are coming down, the excess A must solidify, and as we are coming down, the liquid becomes richer in B by depositing crystals of A in the above step. So, as we are coming down, you will have liquid becomes richer in B and you get out the crystals of A solidifying out, alright. And as you are going from 1 to 4, the amount of pure solid A increases gradually by continued precipitation of solid A from liquid. At XE, that means at this position, remaining liquid. So, what happens is, by the time you reach here, the remaining liquid would have reached the eutectic composition, and that would go through a eutectic reaction and then solidify into mixture of A and B. And we have seen that what is the weight fraction of the liquid just above this point. The weight fraction of liquid weight fraction we have just now calculated, that is equal to 20 divided by 60, that is 33.33%. So, this 33.33% liquid is at eutectic composition at eutectic temperature, and hence it solidifies at that particular instance. So, so if you have alloy 2, 33.33% of that alloy when it is solidified will be in the form of eutectic mixture of A and B. So, remaining 66.67% would have already precipitated as A. So, the result is 66.67% primary A, which is also known as pro-eutectic A. The primary A also has another name, pro-eutectic A. That means, this A has formed before the eutectic reaction has taken place. That is why it is called pro-eutectic A, and the remaining 33.33% will form eutectic mixture due to the eutectic reaction of the remaining liquid, which is 33.33% in weight, and that transforms to solid A, alternate layers of solid A and solid B, that we are calling as eutectic mixture. And now let us look at alloy 3, which is exactly similar, except that if you draw a tie line at point 3, this tie line hits the solidus at pure solid A. That means, the solid phase should be pure solid B, and hence the solid phase that is precipitating from the liquid should be pure B. That is why it is pure B. Now, you understand why we have written liquid plus A here, because when you draw a tie line in this region, it will hit the solidus line at pure solid A, and hence it has to form pure solid A. Here it will hit the pure solid B line, and hence it has to form pure solid B. So, all the alloys here will have pro-eutectic B, that means this gray line, gray one is what we call pro-eutectic B, and by the time you reach at point G, again your liquid solution will have the composition of eutectic solution, eutectic composition, again the remaining liquid solution will transform to eutectic mixture of A and B, all right. So, when we are talking about this, when we have a liquid solution which is reaching eutectic composition, at the eutectic temperature it has to go through this eutectic reaction, and the liquid should transform to two solids, okay. And in general, the eutectic mixtures in general, not for only type 2 alloys, you can also have eutectic mixtures where you have partial solubility in solid state and so on. So, in general, the eutectic mixture might consist of two solid phases, and those two solid phases that we are talking about can be two pure solids, like in the case of type 2 alloy that we have looked at, or two solid solutions, or two intermediate phases, or any combination of the above. You can have one solid solution, one solid, one intermediate phase, one solid solution, one intermediate phase. All that it will have to do is the liquid solution transforms to two solid phases, all right. Okay, so with that we have looked at the important reaction called eutectic reaction, which happens at constant temperature, but it is not congruent, because after the transformation, the liquid transforming to two solids, the compositions of the solids and the liquids are not the same, and hence it cannot be called as a congruent solidification process. Okay. So, with that we have understood the type 2 alloys, and in the next class we will look at type 3 alloys. Thank you.